Hi, everybody. I wanted to add a little bit more to your study for the thermodynamics unit because I realize now that the module does not really address heat of solution. It does a great job of addressing heat of the reaction. And you know that a reaction that releases heat to the environment is an exothermic. The bond energy that it used to have when the reaction happens creates new bonds, and energy that had been stored in the previous arrangement is now released to the environment. So we say that it gives off energy and it has a negative sign. Reaction that requires heat from the environment to drive it, like photosynthesis, those things are endothermic, they're energy consuming. The new arrangement is storing more energy in the bonds. For this example was lead combines with sulfur to make lead sulfide, and that would be an arrangement that has more energy stored in the lead sulfide than in the separate atoms. All right. And when you are trying to find this, and we talk about the heat and we compare it to the number of moles of a material, that ratio we often refer to as enthalpy, and its unit is in joules per mole, or usually kilojoules per mole. So I think they do a great job with the example, but then we get into specific heat, and we are measuring an environment when we measure a specific heat, and we're dealing usually with water in calorimetry as the material that is supplying or absorbing energy that was once in an arrangement. But we're not having a chemical reaction when a material dissolves. We're having an energy exchange with the water and the material that's being dissolved in it, and we refer to that as heat of solution. A little delta H subscript solution, SOLM. And for example, a 1.5 gram sample of ammonium nitrate is added to 35 grams of water, and the temperature drops. It went from 22.7 to 19.4. What is the heat of solution? So we want to look at this as the energy change per mole of material being dissolved, the solute. So the first thing I need to know is how many moles of solute I have, not water. And then we can use our relationship of the mass that is changing temperature, the specific heat. We will assume of the solution to be exactly that of water, because in proportion there's just so much water that any variance of specific heat in that small amount, what was it, a 1.5 sample of ammonium nitrate versus 35 grams of water, the specific heat of water just totally outweighs it. So we'll use the specific heat of water, and then we'll measure the change in temperature of the water. We can't measure the internal change in temperature in the solute, ammonium nitrate in this case. So the mass that is changing temperature is the total mass of both solute and water. We're going to assume the solution is going to have the same specific heat as the water, and then we'll measure the temperature change, and that will give us our energy. And I did some quick math and did that out, and I got an exothermic reaction, or energy that was because the temperature dropped, we wound up with this value being a negative. And so we have final minus initial. And so now we want to determine the heat of solution, and that 504 joules change divided by the moles of ammonium nitrate, and gave me this value. Now, I thought that something that was negative was exothermic, but this was this got colder, it sucked energy in. This was a change of energy left water and went into this situation. So what we do is look at the heat loss versus heat gain. So let's look at this as the heat that the water gave up is the exact same amount of heat that was gained by the crystal lattice of ammonium nitrate to get it to break apart and dissolved. But heat lost and heat gain, well, they have different signs. So we always talk about those being opposite. The heat lost by water is equal in magnitude and opposite in sign of the heat gained. So that's where you get to get rid of the negative sign and turn it into a positive sign, because we're going to focus on the solute than what's happening to it. So since this was a negative number, this becomes a positive. So we had that negative number. Where did it go? So we said this was negative 26.85 equals the opposite of negative 26.85. The opposite of a negative is a positive 26.85 kilojoules of per mole for the heat of solution for ammonium nitrate.